Hey everyone, how goes it? Welcome back to CSCE552 Game Development. I'm your instructor, Dr. JJ Shepard, and today we are going to continue our discussion around game development. In the past lectures, we have focused on the concepts and roles related to game production. We began discussing game development in a previous lecture. Today, we continue this discussion. We turn our attention back to the programmer and continue discussing elements related to the technical design document. We explore more about game programming today. In a previous lecture, we discussed some of the values and concepts related to software engineering. Creating a video game is an exercise in software engineering. The software development process helps to plan and manage the tasks required to create software. A software pattern is a general, reusable solution to a commonly occurring problem within a given context in software design. Some common software pattern categories are structure patterns, behavior patterns, creator patterns, and concurrency patterns. We then focus on a particular behavior pattern used frequently in game software called the game loop pattern. The game loop pattern helps us to organize the game's behavior into common occurrences. Each game loop iteration progresses the game. The event step involves gathering information about occurrences that have happened since the last game loop iteration and applying necessary actions related to the event. User input, collision detection, message handling are common events. The update step modifies the data periodically based on the previous event's data. Moving the player, destroying an asteroid, collecting a coin are common tasks performed during the update step. Finally, the draw step displays the results of the update. In games, a frame is an abstract unit of time between each game loop iteration. Typically, one game loop iteration is equal to one frame, which is equal to one turn sequence iteration. Each frame progresses the game. Real-time games mean that the frame progression matches closely to actual time. Sports, real-time strategies, platformers, etc. are examples of real-time games. Turn-based games mean that the frames progress only when a certain criteria is met. Role-playing games, chess, etc. are examples of turn-based games. There are steps that may appear to exist outside of the game loop pattern that we need to consider. The initialization event is when all the data or resources for the game are created and set to default values. This event only occurs one time, and it is to start the game loop. Within game code, this usually corresponds to a programming function called start, begin, or init. In contrast, the finalization event is when all the data is deallocated from memory. This occurs one time to end the game loop. In code, this usually corresponds to a programming function called end, stop, or destroy. As both of these events only occur once, they could be considered outside of the game loop, but in the end, they are just very special events. This concept can be used to create most games. However, if we were to create a more advanced game, then we need to consider some additional design and planning. More game features require more sophisticated software structural organization to better organize the behaviors shown in the game loop pattern. Speaking broadly, video game or just game software is the entire collection of game-specific code, libraries, systems, and engines that compose a video game. The game software system is the code which runs or drives the game. Typically, it is foundational software that calls or invokes the game loop pattern functions that we write in the game-specific code. It contains software libraries used to write the game-specific code. However, this is commonly considered separate from the game-specific code. as mentioned, that it is foundational code that we build our specific game from. A game engine provides many of the features common in most modern games. We do not need a game engine to make a game, but as a developer, it can speed up the process. We keep in mind that game-specific code is the software specifically developed to create a game. It is separate from the game software system. Most commonly, it uses provided features and programming interfaces provided by the game engine. A game engine is a software framework for developing games. It includes necessary software libraries and supporting programs. The engine contains graphics libraries, a physics engine, input manager, audio manager, message passing, and etc. Once more, a game engine is not required for making games, but it may speed up development time. In most cases, the game engine can be considered the same as the game system. They both contain the necessary software libraries to create a game. They both are in charge of executing the game loop pattern. Some non-typical games may require the use of software and additional engines that exist outside of the context of a single game engine. We keep in mind that the game software system is a broader concept, and game engines are a more narrower implementation. Understanding all of this, today we begin discussing how game software structures work. Game software structure can be viewed in a slightly different way than the most typical object-oriented design software. Entity Component Systems (ECS) puts more stress on composition over inheritance. It focuses on not what it is, but what it does. We also keep in mind that composition was another version of the association or the has-a relationship between classes. This is related heavily to the concepts in the observer pattern or mediator pattern. The component allows a single thing or behavior to span multiple domains without requiring specific relationships to each other. It is a decoupling pattern and has much in common with the composition pattern, where programming objects are composed of other programming objects. Component-based development emphasizes the separation of specific functionality with respect to a wide-ranging functionality available throughout a given software system. Components for a game are classes of behaviors. We create classes of behaviors instead of classes of things. This is opposed to hard-coding functions or methods within a large monolithic class, meaning writing everything in one programming file or writing all the code in a main method. The code for the components are based on the game loop pattern. Separate functions for events, update, draw are expected. Typically, within a game engine, there is a component programming interface for which all components implement the game loop functions. Game objects are the abstract nouns in a game. Every thing in a game is a game object. Every object, player, every enemy, every rock is a game object. Game objects are considered entities in relation to the entity component design. They are simple containers for components. In many cases, game objects may be considered components themselves. Generally, classes are not specifically created for different game objects. There is no class written for player, for enemy, for exploding barrel, or for heads-up displays. Game engines commonly have a universal game object data type, which is not intended to be extended via programming inheritance, but instead just acts as a simple container for components and some additional metadata. Game objects are differentiated based only by what behaviors they may perform. The difference is not the data type, but rather how it behaves. By using this structure, it allows for functionality to be abstracted. Many game objects perform the same actions, so they may share the same components. We can see both player and enemy move and draw. We can consider writing one class move and another class draw and simply add those to the player and the enemy game object. The component's attributes may be different in each instance, but the component does the same action. A player's speed and an enemy's speed may be different, but they still move the same way. From a functional standpoint, they do the same actions, but with different values. Game objects may swap in and out different behaviors. The flexibility of it being decoupled can allow some game objects to either gain or lose abilities. Writing game code requires understanding what are the nouns, things, and what are the verbs, actions, and behaviors in the game. One way we can start doing this is by noticing the nouns and the verbs when reading through the game design document. By categorizing the nouns and verbs, this assists in writing the technical design document. Game code is generally composed of game objects, nouns or things, components, verbs, actions, and behaviors. This becomes the foundational structure of games. We keep in mind that communication is fundamental to all parts of this, and as programmers, we are learning to speak to the machines using programming languages. By identifying the nouns and the verbs, we may speak more clearly to the machines in the same way we speak to people. When we are designing games, it may be useful to draw out the concepts so that ourselves and especially others may understand how to create the game. In software engineering, we are aware of the Unified Modeling Language or UML diagrams which help us to design software. A component diagram is another UML diagram which demonstrates how components are connected, forming a larger system. It is very similar to a UML class diagram. It is a specialized version demonstrating provided and required programming interfaces. Components are typically drawn as a box with its identifier. The phrase component, or comp, is typically placed in the box as well. It may also have an icon composed of a larger rectangle with two smaller rectangles centered on one of its edges. Component diagrams can be created in a variety of ways. Components connect to each other using programming interfaces. We keep in mind that programming interfaces are not the same as a user interface. These instead create rules for other programmers by establishing expected functions or operations that are to be implemented. Through these connections, the components communicate to each other. One way to model this is by using a ball and socket connector. The ball represents what the component provides, information or functionality. The socket represents what the component requires. Again, information or functionality. Above, context can be provided over either the symbol to better describe the relationship. This helps us better understand what it needs and what it provides. These relationships can be drawn from component to component or from game object to component. Game objects require specific behaviors to be provided. This can begin to get messy very quickly, as game objects are more of a container in concept. We may consider designing it this way. We understand that components may be composed of other components. As mentioned before, game objects are components which are composed of other components. These internal components can be demonstrated by enclosing them inside of a larger component. With large systems, like games, this can create a better understanding of how the actions can be grouped into these structures. For a game code design, it is useful to further differentiate between a game object and the component. We can use GO to represent the game object and component or just comp to represent the behaviors. Using this, we can establish what game objects need to do by enclosing them within the game object structure. The internal components are then connected together to create the game object. Typically, we focus implementing the game code through the components and their provided interfaces. The game objects and their components are smaller parts of the overall game system. In game design, we discussed how all games are systems. Commonly, the game system is the code which runs or drives the game. It is in charge of calling the functions related to the game loop pattern. These function calls can be considered event messages that are sent to each game object, then delegated to each component. We notice a new type of connection between the connectors. This is a slightly different kind of relationship that is not as strong as the connection between a ball and socket. This kind of system focuses primarily on broadcasting messages to corresponding components. We know this is based on the concepts related to the observer software pattern. This software behavior pattern creates a one-to-many dependency, so that when the state of the object changes, the dependent objects are then notified. This is great as one message may be delegated to any number of components. So for instance, init, events, update, draw, and final can all be broadcast from the game system to each game object. Then each game object then delegates those messages to each component to handle the steps separately and differently. This implements the game loop pattern. In addition to the game loop pattern, the game software system also is composed of libraries, other systems, and programming interfaces. It provides the game developer with features commonly found in games, such as user input interfaces, physics systems, and other useful software libraries. The game software system can be considered the game engine in most cases. Now, with this in place, I reiterate that the dashed lines represent delegation of the required action to a provided function within each component. Delegation meaning entrusting a responsibility, or for our purposes, delivering an event message. This is an event message that is broadcast to all the components within a game object. One event may have code handling it in several different components. The components handling these events can be considered listening for these messages. This delegation is used so that for one event message sent, it may be handled by any number of components. The same event may be handled differently by many components. Getting hit by an enemy's attack, both will reduce health and knock the player backwards. This one collision event will be handled by a health system component and a move component. A larger example of this is an update may be different from component to component, but they all still must update each frame. Consider in a 3D game, the first-person move component is going to have a different update than a look-around component. They are two actions that both update, but both update different aspects of the game. As components are commonly implemented by a programming interface, these functions are assumed to be written in the component's code. As mentioned, the programming interface for a game component typically has functions representing parts of the game loop pattern. Commonly, these are called events update draw. We also see some more specific events such as init and final usually as well. Keeping all of these common messages in the diagrams makes for a messy design, so there are some assumptions that are made for the sake of cleaner designs. The game system is composed of a collection of components called game objects. Game objects are composed of behaviors called components. To make it cleaner, we place one structure within inside another structure. The game system follows the game loop pattern, meaning that it handles the events for each game object and for each component within. It then updates each game object and for each component within. Afterwards, it draws each game object and for each component within and continues looping. With this understanding, we typically omit drawing the game software system's events in our structural designs. It is my academic duty to explain the classic ways to represent entity component systems and all the concepts related to design. However, speaking bluntly, we are making games and not just diagrams about games. In my professional opinion, these structural diagrams can be further simplified without loss of detail of design. First, we can remove the need for sockets and joints and just have simple associative arrows between components that show specific events. This can be both related to a specific event message that is sent from one component to another, or require data access where one component requires the information from another. While the usage is slightly different, we can use just one kind of arrow, a solid arrow, demonstrating the dependency and relationship. When creating a technical design document, it is important to have details regarding the game objects and components. For each game object, it can be useful to provide the name or identifier of the game object, a description, a brief summary of what the game object is and what its roles are, comments, any additional comment related to the GOs. There will be more details when discussing more advanced structures such as tags and categories, and whether or not the GO is prefabricated or unique. For each component in the TDD, we provide the critical information regarding its functionality. This includes the name of the component, a description, a brief description of what the behavior this component provides, comments, extra or internal data or functionality that assists the component, commonly not put in the component diagram but may be found in a UML class diagram. Optionally, flowcharts can be useful to demonstrate the behavior of a component visually. We take the information from the technical design document and start writing or implementing the components. The designs in the TDD are not overly detailed and leaves interpretation up to the programmers. With our knowledge of structure and behavior components, we can now more thoughtfully write the code. With this knowledge and our own development experiences, we can understand that components only need to implement functions specific to its purpose. Not every function needs to be overridden. When writing the code, we consider that each of the steps of the game loop pattern and what it addresses. Events. What message are we listening for? Update. How does that change the data? Draw. How do we display this change? Components may only need to implement one of the common game loop functions. For the technical design document, game objects and component diagrams are preferred over other types of structural diagrams. Know that there are many kinds of diagrams used in software engineering. Creating a component diagram that demonstrates how to put it together while also leaving some interpretation to the programmers. Alternatively, creating a UML class diagram shows how the code is constructed. We are not going over creating a UML class diagram as more often than not, it does not serve a very useful function in game development. However, there are some cases where creating one of these diagrams may be useful in showing some more advanced structures related to games. Now, we're going to take a look at this structure by using a previously developed game concept. We are once again going to use the high-low game, but this time examine how to structure it. We have seen this example in previous lectures, so we're going to skip over the details and just focus on how we can apply the game object and component structure. Remember, a good place to always start is noticing the nouns and the verbs in the text. Nouns become game objects and verbs become components. First, we can immediately identify the game objects as they are listed in the material section. Both the player and the referee are the only two game objects in our system. This is a good time to note that a referee acts as a game official. This game manager may appear in many different forms in the future, but the concept is still the same. We can now start seeing the components as the actions related to the game. First, we see within setup that there are the behaviors required to occur during the initialization event. We keep in mind that this structure is following the game loop pattern for behavior. We see this continued in the turn sequence. Each of these steps have been grouped together into the behavior and will follow these steps: events, update, and draw. Thinking about how these are grouped, we can start understanding that the main actions seem to be picking a secret number, making a guess, checking the guess, and informing the player. When we associate the behaviors with the objects, we can then group them together with the game objects and their components. In our example, the referee is in charge of picking a secret number, checking the guess number, and displaying the output. We can see the referee game object contains the components pick secret number, check the guess, and show output. These are all related to the abstract behaviors that the referee is in charge of. We can see the associative connection between the components where after picking the secret number, the referee must inform the player by showing an output. In a similar way, after the player's guess has been checked, the referee must once more inform the player. Both of these relate to the associative relationship between the two components and are defined above the line as inform the player. Looking to the right, we notice that the player has a single component, user input. This component is then connected to the referee's check guess component. We can assume that this is a special event, just like informing the player, that is updated and drawn. Looking at this design, we can start to see how we can improve and simplify what we have. We notice that components pick secret number, check the guess, and show output are all behaviors related to the secret number data, the information that was randomly picked and then checked against the player's guess. More to the point, those separate behaviors seem to relate to the game loop pattern steps, events, update, and draw. We may keep them as separate actions, but it makes more sense to group them into a single component where we organize the separate actions into the events, update, and draw steps within one component. This simplifies the overall design as now we have less components. However, there is a trade-off. More components can make structural designs more complicated, but it makes the code more flexible by modularity. Modularity is the way that components within a system can be separated and recombined in different ways. By combining these separate behaviors into one, we reduce our code flexibility, but simplify the overall design and increase the performance. The other trade-off to consider is having to pass data from one component to another takes real, practical time. So we can skip these steps of having to transfer the data before checking it, then it increases the overall performance of the system. We must always be aware of trade-offs of time and space and ensure that we are designing solutions appropriately and not over-designing them. This ends up being the structural design for the high-low game. It is not terribly exciting as the game did not require a complicated design. In many ways, it is more useful to see this in terms of the behavior rather than the structure. When we examine the behavior with the structure, we can start seeing how this comes together. The referee is the game object that contains the component Secret Number Manager. Within this, we see the different events, update, and draw steps in the component. This is the design that we used before, and most of it is featured in the referee's code. The user input component can be viewed as a flowchart as well. This one is not as complex as the referee, as it only features the operational rules providing a guess. We can assume that these events, and when the game first starts, we set up whatever user input system we need. A keyboard input, controllers, touch controllers, motion controls, etc. Then this component listens for the user input. In our case, it is waiting for a number to be entered in through a command line interpreter. Once this event happens, then the guess value is passed to the referee. Creating the game object component structure and combining this with the flowchart showing the behavior of the component is a great way to communicate your ideas effectively. These details are very useful within a technical design document. This was a simple example of a game, but understanding the structure helps to create something more advanced. With this in mind, we take a look at a more advanced game example. This one is very different from the last example as it's not turn-based, but it is a real-time game that features interactive movement. However, this can still be designed effectively using the game object and component structure and using the game loop pattern. Our problem is to create the game Table Tennis for Two. We're going to assume that the full game concept has been written out as a game design document or wiki, which contains all the formal and dramatic elements. You can find the example of this wiki included in the course notes. From the wiki, we can derive some requirements. Two players must be able to control two different paddles simultaneously. The players may only move their paddle up or down. A ball starts in the center of the board each round initially. When one player chooses to start the game, then the ball will choose a random direction and a fixed speed to start moving. The ball must be able to bounce off the player's paddles and boundaries of the screen. When the ball bounces off the walls, it must reflect 90 degrees from its incoming direction. When the ball bounces off the player's paddles, then its reflection angle is based on the center point of the paddle and the collision point. When the ball collides on either of the player's goals, then the other player scores a point and the game resets for the next round. A referee keeps track of the score, and the first player to receive 10 points wins the game. We can start seeing the game objects when observing the nouns in the requirements. We see two players, a ball, the environment being the walls and the goal, and finally the game official or manager called the referee. We can start seeing the components by noticing the verbs. Focusing on what was related to the player first, we notice that some of these can be related to very simple concepts. User input is needed to access the controls and apply them to the paddle. Position, rotation, and scale is considered a special kind of component called the transformation. We will go into more detail about the importance of this component in a future lecture. We also assume that we need collision detection, which is typically handled by a component called a collider. For now, we assume that this is a very simple geometry like a circle or a box that will detect collision between another collider. We can see one way to draw this component diagram showing how each of the GOs are sharing the same components. We can also view it from a different way that shows more of the interconnections between each of the components. Both ways to draw this is valid, but typically it is more useful since it shows the interconnections within the subsystem. We can also see how the user input moves the player by updating the transformation component. We also see how the collider and the sprite component need access to the location provided by the transformation component. All of these interconnect together with the event messages and data access. We also notice that the two structures are identical, and we can consider a way we can combine these two into a replicatable structure. This is called a prefabricated or prefab game object, where we create it once and then replicate it many times over. This is the same concept as creating a programming class that create instances that we call objects. We can reduce the complication of the design by using one instance and noting that it's a prefab in the TDD. We can also put prefab beside GO, but this is optional as long as it's noted in the TDD's GO description. Now we can see the same for ball. Here's how we can design this game object. Once again, we see the interconnections between each of the components. We notice that the collider detects the collision, but the handle the goal collision is handled by the ball movement script. We consider the ball movement component to be listening to the collider. When these messages are sent to the collider, it will broadcast it to any component listening and in turn will handle it. Now we see this with the referee. Notice that we have called its component the scene manager. This is a commonly used concept that represents the roles of a game official, otherwise known as a referee, within the game. The key idea is this role enforces the constitutive and some of the operational rules of the game. We can see the referee simply diagrammed here. This is where we need to start putting the other game objects together to start seeing the bigger picture. Directly related to the referee are the goals. We can see here how we created one game object, and knowing that we are going to make it into a prefab, there are two different goals. Regardless, the goals need to be able to detect collision with the ball object, and when this occurs, it sends an event message to the referee saying a point was scored and by whom. Now, we can put the rest of it together and see the overall structure. This helps to demonstrate which game object has which components and how they are all related. However, this does not describe how the components are implemented, and this would be more appropriate for a flowchart. We should consider using both that describe our designs. In this lecture, we demonstrated the ideas related to the structure of the game code by introducing and demonstrating the game object and component structure patterns. This structure is fundamental when understanding how to create games, and we will be exploring this throughout the course. With all that being said, get structured, and I'll talk to you next time. Now it's time for a bonus round. What is a game engine? A game engine is a software framework for developing games. It includes necessary software libraries and supporting programs. What is game code, and how is it related to a game engine? Game-specific code is the software specifically developed to create a game. It is separate from the game engine. What is a game component? Components for games are classes of behaviors. What is a game object? Game objects are simple containers for components. Where must we put details and diagrams about game objects and components? In the technical design document. Now it's time to look ahead using our forward vector. Now we get structured by looking at the details in the game design document and start considering how this will become the game's code used within the game engine. First, identify the game objects by looking for the nouns in the GDD. It's good practice to look for common game objects like players, referees, also known as game officials or game managers, and also enemies. From there, identify the components by looking for the verbs in the GDD. Next, create game object and component diagrams which associate the game objects with their behaviors and relate other game objects with each other. Finally, create a game object and component list and include this with the TDD. With this focus on structural design, creating a game will take no time. Now, with all of that being said, I'll talk to you next time.